Hello everybody. Here is learning target 3, describing end behavior using limits. So first of all, what is end behavior? End behavior is how the function behaves, what y value the function is approaching, all the way to the right and all the way to the left. So all the way to the right means when x is approaching positive infinity, when x is getting really, really big, what y value is the function approaching? And then on the left-hand side, when x gets really, really small, like negative 1 million, when x is negative 1 million, where's the y value? Is the y value way up in the sky, way up to positive infinity? Or is the y value way, way down to negative infinity? Sometimes the y value approaches a single number, like 3 or negative 2 or whatever. So end behavior, what is happening to the y value when x gets really, really big and when x gets really, really small? Both directions, left and right. And to express that, we use what's called limit function, limit notation. So this is the notation, LIM for limit, and you read this as the limit of f of x is, whatever the answer is, as x approaches infinity. So what this is trying to say is when x approaches infinity, so when x gets really, really big, in other words, when you go way to the right in your graph, what y value is being approached? The y value is f of x. And then the other side too, when x approaches negative infinity, so when you look to the left, what y value is being approached? And there are basically two families that you're responsible for, polynomials and rationals. So this example really quick, this polynomial, there's a turning point here, 1, 2, and then a little inflection point here. So it's a third degree polynomial, maybe a fifth degree polynomial actually. But anyway, when x goes to the right, so as x gets really, really big, where's the y value? Well, we can assume that this graph is going up to the right forever. So when x gets really, really big, the y value is also really, really big. And in fact, it's approaching infinity. On the left-hand side, when x gets really small, the y values are going down. When x gets small, so does y. So as x approaches negative infinity, the limit of this function also approaches negative infinity. Rational functions sometimes behave differently, sometimes not. This rational function, it looks like it has a horizontal asymptote at y equals 2. Since this is 10, this would be 2, 4, 6, 8, 10. So as x gets really large, it looks like this value is getting closer and closer to the value 2. So the limit of this function as x approaches infinity is 2. And as x approaches negative infinity, the y values are getting closer and closer again to 2. Not infinity or negative infinity, but a real number. So again, this is just reiterating what we just talked about. When x approaches negative infinity, you're looking to the left. When x approaches positive infinity, you're looking to the right. And your answer comes here and here. What's going on to the graph when you're looking way to the left? What's the y value? What's happening to the graph when you look way to the right? What's the y value? Now let's review some basics about polynomials, stuff that you learned in Algebra 2. The key thing here is to focus on the dominant term. Terms are separated by pluses and minuses. So I got 1, 2, 3, 4, 5 terms here. And the dominant term is the term that has the largest degree on the exponent, on the variable. So positive 7x to the fourth is the dominant term. In example 2, it's negative 1x cubed. That's the dominant term. In example 3, it's positive 1x cubed. That's the dominant term. Usually the dominant term is listed first, but it doesn't have to be listed first. It usually is. But I'm telling you, you should look for the exponent on the variable that is the highest. That is the dominant term, because I call it dominant because when x gets really, really big, You take that big number and you raise it to the fourth power. So it gets very, very large very quickly. So x to the fourth power, when x is a million, raising that to the fourth power would the contribution from this term would be so heavy, it would contribute so much to the y value that it would just completely dwarf any contributions that these other four terms make. So for example, even a smaller number like 100, let's say x equals 100. Well, this term contributes 300 to the y value because it's 3 times 100. This term just takes away 99, but adding 300 and taking away 99, you're still up 201. This one takes down 100 cubed, which is a lot. This one subtracts 9 times 100 squared, which is a lot. But none of those four compare to the dominant term. 100 to the fourth power is a huge number. And then you're multiplying it by 7, so you're making it even larger. So in the end, when x approaches infinity, when x gets really, really large, the only thing that really matters is what is the dominant term doing? And when x gets large, this thing gets really large. So it pulls up the y values up to infinity. And when x gets really small, so like negative 100 or negative 200 or negative a million, really, really small, well, negative a million to the fourth power, you have a negative times itself 4 times. So all the negatives cancel out, making it, again, a really, really large positive number. So to the left, the y values also approach infinity. To practice this on your own, I would just look at the polynomial first and then try to think through what happens to the right and what happens to the left. It's either going to approach infinity or negative infinity. It's for polynomials, that's always true. It's either going to approach infinity or negative infinity. This example approaches infinity on both sides. But then once you thought it through and make your choice, go to Desmos and graph that and see if it agrees. Example 2, here's the dominant term. So when x gets really large, again, dominant term means these other terms don't contribute. When x gets really, really large or really, really small, these other three terms don't matter. It's all about this one. So when x gets really, really big, you're cubing a big number, which makes it even larger, huge. But then the last thing you do is multiply it by -1. So -1 times a really, really big number turns out to be a really, really small number. So as x gets really big, this whole function, the y values will get really, really small. This dominant term drags down those y values. What happens when x gets really, really small, like negative a million? If x is negative a million, well, cubing negative a million, those negatives don't cancel out, do they? You're left with a negative 1 with a bunch of zeros after it, whatever a million cubed is. But then you're also multiplying by -1. So it's -1 times a negative number, which makes it a positive number. So when x gets really, really small, this term right here gets really, 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 really large, really positive. So it pulls up all the contributions from these three. So it pulls up the y values up to positive infinity. Here, same thing as the second example, except it's plus x cubed. So when x gets really large, you're cubing that number, so it gets really large still. And then you're multiplying a large number by +1, so it remains large. So when x gets big, so does the y. What about when x gets small? Well, when x gets small, so does the y, because negative a million cubed, the negatives would not cancel out. So you just have +1 times a negative number, which is still negative. So that's why it goes down to a negative infinity. You may have learned in Algebra 2 that it's about the degree and the leading coefficient, terms like that. So here, the dominant term, so the biggest degree, in this case 3, if the degree is odd, then the end behavior changes. So notice, on one side it goes down, but on the other side it goes up to infinity. And here's another, the degree is odd. So one side went up, the left side went down. If the degree is even, like it is here, 4 is an even number, then the end behavior is the same on both left and right. This one happens to be going up in both directions, but you could easily go down in both directions. If I just change that to a minus 7x to the fourth, both of these would be negative infinity. This example is different from the previous one. It's still a polynomial, but it's not multiplied out. And you shouldn't have to multiply this out to figure out the answer. What degree is this polynomial? If you were to multiply it all out, what degree would it be? It would be a fourth degree. This x plus 3 squared would automatically makes this x and x squared. So this chunk right here would already be x squared. You multiply it by x, so now it's x cubed. And you multiply it by this final factor, and you would have x to the fourth. So the very first term, if you multiplied this whole thing out, the very first term would be negative 1 x to the fourth. Negative 1 x to the fourth. Now, to the fourth, that's an even degree. So both sides are behaving the same way. Here's what that graph looks like. And it's negative 1 times x to the fourth. So when x gets really, really large, you're raising that large number to the fourth power, and then you're multiplying it by negative 1. So it pulls it down to negative infinity. And when x gets really small, like negative a million to the fourth power, all those negatives cancel out, so it's positive. But then remember, you're multiplying by that negative 1 in front. So it again pulls it down to negative infinity. Rationals. Similar thought process, but different enough. Rational functions, the root word is ratio, so you're comparing to, you got two polynomials one's being divided. And again, the dominant term. Here, it's that first term, 3x cubed in the top, and in the bottom, it's 4x is the dominant term. In the second one, you got 3x cubed in the numerator and 4x cubed in the denominator. And in the third one, you've got 3x cubed in the numerator and 4x to the fourth in the denominator. All three of these examples are similar. The only thing I changed was the exponent on the denominator. All right, let's start with the bottom one first. That's the easiest one to understand. When x gets really large, again, only the dominant term really matters. When x gets really large, this is going to be a large number for sure, because x cubed times 3 makes it very, very large. But it gets totally outpowered by this, x to the fourth. X to the fourth rises more quickly than x to the third. So when x is a million to the third power is huge, but it is no way compared to a million to the fourth power. This is just much larger by a million. So when x gets really, really large, the denominator here gets large faster than the numerator. So this is a case where you are dividing by a really big number. And tell me, what's the consequence when you divide by like a really, really big number? What's 1 divided by 99,999,999? If you have one pizza and you have to feed everybody in Europe, how much pizza does each person get? They basically get nothing. They get like a crumb. If you take 1 and divide it evenly into this big number, you basically get nothing. That's what's going on here. When the degree in the denominator is larger than the degree in the numerator, your end behavior will always approach 0, left and right, because that denominator just overpowers the numerator, and the final result is just 0. This middle example, the degree in the denominator is not larger. In fact, both degrees are equal. So when x gets big, they are both getting big at almost the same rate. Because they're both being cubed. The only difference is the top is 3 times that big number, and the bottom is 4 times that big number. So that becomes a ratio of 3 to 4. So you got 3 billion divided by 4 billion, or whatever, 3 times a big number divided by 4 times an equally big number. So that just simplifies to 3/4. So when the degrees are the same, it's just the ratio of the leading coefficients, which reminds me of this one 2 examples ago. This one right here, our first page. Notice, remember I had a horizontal asymptote at y equals 2? Well, this tells me right away that the 2 degrees on the top and the bottom are the same, but the ratio of the leading coefficients is 2 to 1. This could be like 4x squared over 2x squared, or 2x cubed over 1x cubed, or something like that. Something where the ratio of the numerator to the denominator is 2. Okay, again, when the denominator has a bigger degree, it's automatically 0, because the denominator is getting so huge. You end up dividing by a huge number, which always results in 0. So it's 0 left and right. When the degrees are equal, then it's the ratio of the leading coefficients. It cancels out. It just reduces to 3/4. 3 times the big number divided by 4 times the big number. To the left when x is small, and to the right when x is big. Well, what if the degree in the top is bigger than the degree in the bottom? That means that's kind of like the reverse of this, 99 million divided by 1. So here requires the most thinking. When x gets big, x cubed is really large, and you compare that to 4 times x. X cubed completely overpowers just x to the first power. So the numerator is much larger than the denominator, much larger by a factor of 3 here. So it will not approach a number. It'll just go on to infinity. What about when x gets really small, like negative a million? If x is negative a million, well, a negative a million cubed would be 3 times negative a million times negative a million times negative a million. So an incredibly small number, because those negatives don't cancel out. You end up, it's 3 times negative 1 with 9 zeros, or whatever the case is. It's an incredibly small number. But then you're dividing that by 4 times negative a million. So it's a negative divided by a negative, which is still resulting in a positive. So the result would still be positive infinity. Last slide. Nope, 2 more to go. What is the end behavior of these two? Well, it's a rational function. The degree on the bottom is bigger than the degree on the top, so there is no thinking to be done. It's just 0, because that denominator is getting so big so fast. The end result is a little tiny number divided by a big number, and that always results in 0 on the left and on the right side. This one, not so much, unfortunately. The numerator has a greater degree than the denominator. So when x gets really big, the top just becomes this huge positive number. So when x gets big, the whole function gets big. When x gets small, like negative a million, here negative a million squared, well, those negatives would cancel out. So it would be a big positive number. The denominator would still have a negative, because the negatives wouldn't cancel out. So you have a big positive number divided by a negative, which makes it negative infinity. And then, yes, what is the end behavior here? Well, you have a rational function. The degrees are the same. So when the degrees are the same, they're kind of like equal in strength. And it just comes down to the leading coefficients. The x squared versus x squared, they're equal to each other in strength, but the top is 3 times that number, and the bottom is 2 times that number. So that is a ratio of 3 to 2. In other words, 3 halves. And then what's the y-intercept? We should always be able to find the y-intercept very, very quickly. Here, we don't need a calculator. The y-intercept is always the result of x equaling 0. So if x is 0, this goes away, this goes away, this goes away, this goes away. The only thing that's left is negative 6/5. So the y-intercept is negative 6/5. I hope that makes sense. And please talk to me if you have any questions.